Okay guys, so in this video, I'm going to be looking at a set of questions from an AQA A-Level Chemistry past paper on alkenes, okay? So we've got some isomerism going on, some mechanisms, so let's jump straight into this, okay? As always, pause the video, attempt it yourself, maybe you've already done these questions, go through the mark scheme, learn from your mistakes, okay? Super important in chemistry, all right? So alkenes, let's look at this. So concentrated sulfuric acid reacts with alkenes, alcohols, and sodium halides. Name the mechanism for the reaction of concentrated sulfuric acid with an alkene. Okay then, so this one should be pretty easy, guys. Easy 1 mark, okay? You should know straight away where there's a mechanism involving an alkene, it's primarily going to be electrophilic addition, okay? That's really the only thing that they can ask here. Electrophilic addition. Okay, first mark out of the way, easy 1 mark right there. Let's tick that off. Okay, next question here then. Outline the mechanism for the reaction of conc H2SO4 with propene, okay, to show the formation of the major product, okay? So this is actually a caveat to electrophilic addition where we have 2 products potentially forming, okay? We have a minor product and a major product, okay? And the names are pretty self-explanatory, right? The major product is going to be the product the majority of the time. So what I'm going to do, I'll jump into the mechanism, and then when we get to the intermediate, I'll explain why I did it this way in order to form the major product. Hopefully you guys already know how this works, but if you don't, it's all good. So what I'm going to do is I'm just going to start by drawing propene, okay? Now, as always in these organic mechanisms, you can draw it displayed, structurally, you can draw it skeletally, it's up to you, however you find the best way to do it. I'm just going to draw it showing the important bonds, all right? I'm not going to do display, that's a waste of time. In my opinion, but I'm going to display the most important bonds that I think we need here, okay? So I'll show the double bond, okay? And then I'm going to show a hydrogen coming off of that. And then the methyl group going off to the side in the propene, I'm just going to show like that. And then I'm going to show both of the hydrogens bonded on this carbon right here, okay? You don't need to do that, but I just feel like it's a nice touch because ultimately we're going to either be transforming this carbon right here to have a CH3 or this one right here to have a CH2. So I'll explain that in a second. What's going to happen here, okay? In the mark scheme, it shows a displayed formula, the displayed structure of the sulfuric acid, the H2SO4. I actually don't recommend doing it this way, okay? You can. It's just one extra thing you have to remember, the structure of sulfuric acid. The way I recommend doing it is similar to how you would draw out a hydrogen halide, okay? So I'm going to expand upon that and explain myself. So draw the H right here, okay? Then draw the single covalent bond to the oxygen right here, and then just draw the remainder of the molecule, okay? SO2OH. All right, now you may be thinking, how the hell is that similar to a hydrogen halide? It's because let's say we're doing this mechanism, carrying it out with hydrogen bromide as our reagent, as our electrophile. I would put that like this, right? Okay, now what you can do is you can essentially replace the bromide with the OSO2OH, and it just makes drawing the whole mechanism quicker and easier to remember, okay? Now, let me rub out this hydrogen bromide and get on with the mechanism here. So, dipoles, okay, electronegativity difference. You don't need to show this for AQA, but I'm just going to explain myself a little bit, just in case you guys are lacking on the theory side of the mechanism, okay? So, oxygen right here, group 6, okay, it's going to be a lot more electronegative than this hydrogen. So I'm going to chuck on our delta negative charge right here to denote relative negativity, okay? Next up, our hydrogen has to have relative positivity within this dipole. Okay, that's pretty much how this works. The electrons are going to be pulled towards the oxygen, essentially, within this covalent bond right here, okay? So as I mentioned, you don't need to show this to get the mark. So if you ever get confused, just leave it out completely would be my advice, okay? Now, this region right here, this double bond, this covalent double bond is a region of electron density, okay? It's incredibly negative. So what's happening here is this region of electron density is attracted to the relatively positive hydrogen, okay? And that's going to be our first mark here, okay? Next up then, what happens? Due to the electronegativity in this dipole, this oxygen right here is going to attract the 2 electrons within this bonding pair here onto itself, okay? I don't know why I changed to blue, but there we go. So what I'm going to do next is just essentially break down what happens in the intermediate stage, okay? So drawing my arrow here, okay? Next up, we have to decide what is happening to the intermediate structure. The electron pair that's located within this covalent bond is obviously going onto this hydrogen to form a new covalent bond, and that can be formed on the adjacent carbons within the carbon-carbon double bond, okay? So either this one or this one. Okay, and that will depend on the stability of the structure. So throughout these next few questions, I'm going to explain it and expand upon it, but just to break it down simply, we have 3 different types of what we refer to as carbocations, okay? So I'm going to draw my intermediate and then explain it. So I'm going to show 3 hydrogens here. So you'll notice that we started with 2 hydrogens, a CH2 group. This hydrogen, which was added to the molecule here, is going on this carbon, so it's now turned into a methyl, a CH3, okay? Now what's going to happen here is we have our CH as it was, and then we're going to have our other methyl group here, okay? Now what's going to happen is carbon, group 4, it likes 4 bonds due to 4 valence electrons, so I'm going to have to give this a positive charge because it's lacking a bonding pair here. Now, why did I choose to add the hydrogen onto this carbon rather than this carbon? And this is all to do with stability of carbocations, okay? So if you weren't aware, there's 3 different types of carbocations. There's tertiary, secondary, and primary. Now the reason I've added these right here is I'm trying to explain to you that tertiary is always more stable than secondary, which is always more stable than primary, and that's just how it works. Now, how do I tell from this what is tertiary, what is secondary, what is primary? So looking at this intermediate right here, how do I tell whether it's tertiary, secondary, or primary as a carbocation? And all you have to do is you have to look at the carbocation, okay? And then you have to look at how many alkyl groups are branching off of it or coming off of that carbon, okay? So we have 1 adjacent alkyl group here and 1 adjacent alkyl group here, making it a secondary carbocation. Okay, now what I'm going to do real quick is just draw the other potential structure here, which is going to go off onto our next question, but it will sort of answer it for us, okay? So what is going to happen here is, let's say I kept this this intermediate side, this CH2, let's say I left that as CH2, okay? And then I turned this middle carbon into CH2. So the hydrogen from this was added to our central carbon here rather than our end carbon. And this is just still CH3, okay? Now what we can see is we're going to have to make this the carbocation, in which case it only has 1 alkyl group attached, which makes it a primary carbocation, okay? Hopefully this is clear. If not, just brush up on your carbocations and you should be completely fine. Now, the area which a lot of students actually make this mistake is they refer to the final product as tertiary, secondary, or primary, whereas this isn't the case, okay? It's always the intermediate carbocation that is going to be secondary, tertiary, or primary. I got that in the wrong order, but you get what I mean. So let's rub these guys out real quick and draw our products, okay? So funnily enough, in AQA, they don't actually give you the mark for the product, all right? Which is kind of weird because they ask you to show the formation of the major product, but I suppose that's shown through this intermediate stage here. So all we're going to do is have our CH3 right here. We're going to have our CH, and we're going to have our CH3, okay? Now, I've actually missed something off here in the intermediate stage. We need to show the electrophile coming in and attacking this carbocation, okay? So what's going to happen is we're going to have our OSO2OH, all right? This part of the molecule that was broken off. Now, as I said, this covalent bond broke and donated the pair back onto the oxygen, so naturally we have to show a lone pair on this molecule here, okay? Now, because it's gained an electron, which was originally from the hydrogen, we have to show this as a negative oxygen. Okay, now what's going to happen here is this region is attracted to this positive carbocation, donates its lone pair, forms a new covalent bond, okay, adding itself onto the molecule here, okay. So what's going to happen here is we're going to show that right here with our OSO2OH. Okay, easy as that, guys. 4 marks in the bag. First mark, this arrow. Second mark, this arrow. Third mark for the structure and the correct carbocation position. And then fourth mark is going to be this curly arrow right here with the negative charge on the OSO2OH. Okay, hopefully that was clear. Hopefully that helped you guys out understand the theory a little bit more if you weren't too sure about it. Now in this one, all we have to do is show the minor product, okay? Really easy 1 mark right here. I'm going to show this final structure, but I'm going to shift the OSO2H onto the end because that would mean our intermediate is this guy right here, our primary carbocation. So I'm going to have H2C and then this OSO2OH coming off, and then we're going to have CH2, CH3. Easy as that, okay? That's our 1 mark right there, easy peasy. Okay guys, next question 2.4. Explain why the product shown in your answer to question 2.2 is the major product, okay? So I'm just going to sort of explain myself when it comes onto the stability of the carbocations, all right? So this is a 2-mark question. I'm going to write a brief paragraph and explain it. Okay guys, so brief paragraph right here. So let's read through this. The major product is formed via a secondary carbocation, which is more stable than a primary carbocation that forms the minor product. This is due to the electron releasing strength of 2 adjacent alkyl groups opposed to 1. Okay, now this electron releasing ability of alkyl groups can also be interchanged with the positive inductive effect, okay? There's 2 types, okay? Positive inductive effect is going to push electrons or donate electrons onto the adjacent carbon or whatever functional group is there. And then negative is going to draw it towards itself, okay? In this case, alkyl groups are positive inductive effects. So I'm going to explain this quickly. If you guys that are interested, you can skip ahead. If not, let's say we have a secondary carbocation here, okay? I forgot the H right there. Essentially what happens is these alkyl groups, this is beyond the specification, okay, but all you need to know is that they're electron releasing or electron donating. But what happens is due to the electronegativity difference between the carbon and the hydrogen, okay, we get essentially a very slight dipole forming here. The electronegativity difference is not that much at all. But what happens is this ultimately pushes electrons onto this positive carbon, okay? They release electrons onto it, making it less positive and therefore more stable, and that's how it works. Now, let's say we only had 1 alkyl group here onto this carbon. It's going to have less of an electron releasing strength or character. Therefore, it's going to be more positive still and therefore less stable. Hopefully that makes sense, clears things up for you guys. But yeah. Okay, 2.5 guys, butan-2-ol reacts with conc H2SO4, I keep doing that, concentrated sulfuric acid for you guys reading, to form a mixture of 3 isomeric alkenes. 2 of the alkenes are stereoisomers. So we've got 3 isomeric alkenes, 2 of them stereoisomers. If one of them's stereoisomer, the other one has to be structural. Okay, essentially how it works here. Draw the skeletal formula of each of the 3 isomeric alkenes formed by the reaction of butan-2-ol with conc H2SO4. I did it again. Concentrated sulfuric acid. All right, skeletal formula. Hopefully this isn't too bad for you guys, and you have to give the full IUPAC name of each isomer. AQA absolutely loves this type of question, okay? It's come up in the old spec, current spec a few times now. Butan-2-ol isomers, okay? Now, when we react a alcohol with concentrated sulfuric acid, this is ultimately going to be a dehydration, okay? We're dehydrating it with an acid, okay? So if we have butan-2-ol and it gets dehydrated, all a dehydration reaction is the removal of a water. It's pretty self-explanatory based on dehydration, okay? You're losing a water molecule. Okay, so what's going to happen here is that we're going to get an alkene. It's already told us that, so that's pretty useful. Now, we're going to get 2 stereoisomers, okay? Alkene stereoisomers, the first thing you should think of is geometric. Okay, that's essentially the only stereoisomer we can have here. Geometric, okay? Geometric isomers under the alkene topic, EZ. Okay, simple as that. Okay, within transition metals, cis trans, alkenes, EZ. Okay, just try and remember that. Now, I'm going to focus on the structural one first, okay? So what I'm going to do is I'm just going to draw our butan-2-ol really quickly and then sort of explain what happens briefly. So C, butan-2-ol, okay, OH, and I'm just going to draw the other hydrogen here, okay? Now, within a dehydration reaction, what can occur is it's obviously going to lose this OH. That's always going to happen regardless. But what can happen is we can either lose this hydrogen right here, adjacent this way, or we can lose this hydrogen adjacent this way, and this will change ultimately the isomer that's formed, all right? So first one I'm going to do is I'm going to lose this hydrogen right here on the left-hand side, the start of the molecule here, and form but-1-ene, okay? So that's going to be our structural isomer here, which would obviously form a double bond here. Okay, that's what happens here. So we're going to lose this guy, form a double bond here, and we've still got a hydrogen left here and here. Okay, so I'm going to turn that into a skeletal structure here, which isn't too hard. Hopefully you guys are familiar, just absolute zigzags all over the place. Okay, skeletal, essentially when you're going left to right, it's just a zigzag. And then when you're branching off of it, when you're branching off of it, you go up and down. Okay, that's just how it works. Essentially, that's the easiest way to think about it, all right? So what I'm going to do here is I'm going to draw out our skeletal butene. So it's going to be 4 carbons, so 1, 2, 3, 4. And then we just have to show a double bond here. You can show on either side, okay? So you can show it here, or you can show it here. Either's fine. I'm just going to keep it right there, okay? Now, like I said, our name is going to be but1ene. Easy peasy, first mark in the bag. Let's boop. All right, moving on. Now, I mentioned that the other two have to be geometric because they've sort of told us it right here. If they don't tell you, always going to be the case when dehydrating our butan-2-ol. Okay, now, what's going to happen here is we're going to have either the E form or the Z form, okay? E is going to be across the molecule, so let's draw out our but2ene here quickly and then sort of explain myself. So, with geometric isomerism, okay, if it's Z, same side. That's how I remember it. So our priority groups, which in this case are just our alkyl groups, are going to be on the same side of the molecule. So they're either going to be up here, CH3, or you can just chuck them on the other side of the molecule. Up to you. Doesn't matter if you put them on the top or the bottom. Okay. Now with our E isomer, they're across the molecule. Okay. So one priority group is going to be at the top, one at the bottom right here. Okay. Obviously you can change these over to be on either side. It's up to you. Doesn't really matter which direction you draw it, because when you flip the molecule around, rotate it and stuff, it's going to be that way. Now, be really careful with this. When I said rotated, I might have confused you guys here. You cannot rotate it this way, okay? And that's because of the restricted rotation of the double bond due to the overlapping pi orbitals, okay? We cannot rotate it right that way, but we can rotate it this way, essentially. You can spin it around that way. Hopefully that makes sense and didn't confuse you. So in this case then, I'm just going to draw this skeletally. All right, so many of you may do this, okay? It's exactly what we did in the first step. We just do a zigzag, which is what I said to do, so maybe it's my bad. And then just chuck the double bond in here, okay? This is difficult because ultimately what happens then is that there's a hydrogen going here, a hydrogen going here. So this is technically trans, but it becomes a bit messy and confusing. So what the examiners like to see is they like to see the double bond being horizontal right here, okay? And then what's going to happen is we're going to get a methyl group going off. And then if we start again with the double bond in the middle, they can be on the same side this time. Okay, just try and keep that in mind that with geometric isomers, they like to see the double bond horizontal and then the rest of the chain going off in either direction. Okay, just keep that in mind. So this is going to be our, what is this? E but2ene. Okay, and this is going to be our Z but2ene. 2 extra marks there. Good to go. Okay. Okay, final question here, guys, 2.6. The questions after this were about halides, so I just left it off over here. So focus on alkenes. A byproduct of the reaction of butan-2-ol with conc H2SO4 I did it again, has the molecular formula C4H8O. Name this byproduct, identify the role of the sulfuric acid in its formation, and suggest the name of a method that can be used to separate the product of this reaction. Okay, so although I just said it's alkenes, this is actually an alcohol question, so I guess I'll just chuck it in as a bonus. Now, this question, although many of you may think it's paper 2 because it's organics, this was actually from paper 3, okay? So we've got some synoptic knowledge going on here, and it's actually quite a nasty one from AQA, all right? So let's look at this, okay? Butan-2-ol, this is an alcohol, so our general formula is going to be CnH2n plus 1OH, okay? So ultimately what I can just say here is that our molecular formula to start with is C4H9OH, okay? And we've ultimately transformed that into C4H8O, okay? So here we've lost 2 hydrogens, okay? It's actually become oxidized. Now, when we react butan-2-ol with conc H2SO4, we actually get oxidation occurring. This H2SO4, sulfuric acid, acts as an oxidizing agent. That's primarily due to the oxidation state of sulfur within H2SO4 being pretty damn high, okay? It's actually +6, okay? When a charge is this high, it can actually act as an oxidizing agent quite commonly. Now, within this topic, okay, the oxidation of alcohols, you normally need acidified. This guy is the acid normally, but you also need potassium dichromate. So you need acidified potassium dichromate, and that's just under the specification. But here they expect you to know that this in itself can act as an oxidizing agent, which is pretty mean, but here we are, AQA. Now, what's going to happen here is this a primary, so is butan-2-ol a primary, secondary, or tertiary alcohol? Okay, so it's going to be secondary, guys. So I'm going to rub this out, and just draw it in quickly. Let's change this to CH2, CH2, CH3, and there's going to be OH right here. All right, so we have butan-2-ol right here, okay? Now, as we can see here, just as with the carbocations, you do it exactly the same way as with the alcohol. You just look at the adjacent alcohol groups attached to this carbon, which is attached to the hydroxyl, okay, of the alcohol. So what we want to do here is we want to think back to our alcohol topic and think, okay, is a primary alcohol, when it's oxidized, what is formed? A secondary alcohol, when it's oxidized, what is formed? A tertiary alcohol, when it's oxidized, what is formed? Okay, so I'm running out of a bit of space here, so I can't really say what happens, but primary, secondary, tertiary, okay? Primary becomes an aldehyde with limited oxidizing agent, and then if you allow it to have subsequent oxidation occurring, it goes to a carboxylic acid. So I'm just going to rub this out real quick. All right, so carboxylic acid right there, Q. Now, secondary, going to produce a ketone, no further oxidation occurring, and then with the tertiary, we actually don't get any oxidation occurring. So I'm just going to put 2 crosses here. Okay, a little bit of revision for you guys there. So our byproduct here, when we are going from butan-2-ol to a ketone, it's naturally just going to produce butanone. Okay, butanone. Okay, that is our byproduct. Now, like I already explained, the sulfuric acid can act as an oxidizing agent. So that's just going to be, I don't know about the H there. Oxidizing agent. Okay, done right there. Name the separation method. Okay, so we're producing our alkenes, like we said in question 2.5. We're also producing this ketone. So how do we separate them? Simply going to be fractional distillation, okay? So chuck that in my answer box. Fractional distillation. And there we are, 3 marks on the board. Let's go. Okay, real quick, guys, as I always do most of the time, show the examiner's report and mark scheme, okay? Mark scheme, I'm going to sort of skip over this for a second and focus on the examiner's report, okay? 2.1, I'm going to ignore it. 78% of students gain the mark. Hopefully more gain the mark here, okay? Electrophilic addition, if it's an alkene, just chuck down electrophilic addition, even if you don't even know what's going on, okay? Just get yourself the mark. Now, 40% of students scored full marks. Again, this is quite low. This is quite an easy mechanism. If you do what I said and you remember the H2SO4 as this structure right here, it becomes a lot easier. As I mentioned, you don't need to show these guys. You don't need to show the partial charges, okay? So if you're confused, leave them off, all right? But it's pretty simple to remember, at least I think it is, that if this is positive, we're going to have the attraction between the negative double bond here, the electron dense negative region onto this positive hydrogen. That's just essentially how it works. So I should say relatively positive, okay? This isn't a formal charge right here. Now, what have we got next? When confusion arose, it generally involved attempts to show mechanisms involving water and producing the alcohol, when the final product in this case should be propyl hydrogen sulfate. The most common omissions were the curly arrow to show breaking of the HO bond in H2SO4 and or the negative charge on the H2SO4 minus ion. The bonding order of atoms in H2SO4 was also sometimes confused with structures such as HOHSO3 seen. Okay, that's why I just say, you know what, it's a lot to remember the structure here. You can if you want. Looks like this guy right here with the double bonded O's on the side of the sulfur. Can remember it like that if you like it. But ultimately just do it like this, similar to a hydrogen halide. Easiest way to go. Okay, this bond has to break here. Okay, we can't just accept the whole molecule in one step. It has to break in stages. We have to add the hydrogen on to form our carbocation intermediate, and then we're going to get this coming on. Okay, that's essentially how it works here. So yeah, check out the mark scheme, pause the video, see where the mark breakdowns are. Pretty sure I covered everything. Now, in 2.4, only 17% of students have achieved full marks. And I know exactly why this is, okay? Now, this was only a 2-mark question. So normally this sentence here where it says the major product is formed by the more stable carbocation, blah, 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 which is more stable. this would normally just be 2 marks in itself. So AQA, for whatever reason, decided to chuck this new terminology in here. It's not really new, it's in the specification, you need to know it, but normally in a 2-mark question, you wouldn't expect to have to say it. So my advice to you guys this year, considering alkenes is on the advanced spec, just remember this, okay, in terms of what products are formed, whether it's major or minor. Just remember this whole electron releasing character of the alkyl groups, okay? Or alternatively positive inductive effect right here. Now, obviously, the more alkyl groups are attached, the more adjacent alkyl groups you have, the greater this electron releasing ability is going to be onto the carbocation, okay? Right, what do we have here? This was another question that proved trickier than expected, with a roughly even split between 0, 1, 2, and 3 marks. Butan or bute were often seen as incorrect stems of names, and a very common error was for the same isomer of butene to be drawn twice, with one named as Z-butene. And okay, that's just a mistake, I guess, poor guys. Now, okay, real juicy tip here, guys, real quick. You guys that struggle with IUPAC nomenclature, okay, organic naming, it's actually quite simple once you get used to the rules involved, okay? Normally teachers teach this, but it's a trick I learned and it makes things so much easier, okay? Now, let's look at the typical suffix here of an alkene that we need to know. We need to know this suffix, essentially, okay? Now, when a suffix starts with a vowel, you always remove the E from the prefix, okay? So normally, let's say it's bute something, okay? Now, because there's a vowel present, we get rid of the E. Okay, so it just becomes butene, and then obviously you have to name on which carbon the double bond is. Okay, now let's look at something like a nitrile. Okay, so I'm going to change my color up here to a red. Nitrile. Okay, nitrile is our suffix here. Now, let's say I had, again, butane. So let's say butane nitrile. Okay, now butane is our carbon chain, so 4 carbons, and nitrile is our suffix. If it wasn't a consonant here, you would remove the E, okay? Because there is a consonant, you keep the E, okay? So it would become butane nitrile. So hopefully that's useful to you guys out there that struggle a bit with names, but yes, a fantastic tip, okay? Just focus on what is the suffix. Is there a consonant? Is there a vowel at the beginning? And then you're going to have to switch up the E, get rid of it or not, depending on what the suffix is. Hopefully that's helpful and didn't just confuse you even more. But yeah, keep that trick in mind. It's really helpful. All right, last here, 2.6, butanol was a common wrong answer for the byproduct, and the fact that sulfuric acid acts as an oxidizing agent was not well recognized. Okay, this is expected, okay? This isn't in the spec, the fact that sulfuric acid is an oxidizing agent of alcohols. So it's not surprising there. Normally you would have to, as I said, put the potassium dichromate, acidified potassium dichromate or sodium dichromate, whatever you're using. So it's not surprising, a bit mean of AQA here. Butanol, that's an aldehyde, okay? So if we start with a secondary alcohol, we should know that it produces a ketone when it's oxidized. But if you didn't know it was oxidized, then yeah, you may struggle there and just guess. But hopefully that's not the case. So just keep that in mind. Okay guys, so that's the end of the video. Hopefully you found it helpful. It was a long one, so hopefully you stuck with me. Hopefully you found it useful. If you did, please like the video. It really helps the channel grow. Subscribe for future maths and science content. Best of luck in your exams. Peace.